Yeah, good morning to all of you. In this lecture, in previous lecture, I have discussed the concept of Lagrangian and expression of Lagrangian in different coordinate system. In this lecture, I will discuss the Lagrangian equation of motion, and what is the concept of cyclic coordinate and generalized momenta, which is very important concept for the competitive examination point of view, like NET, GATE, TIFR, and PhD, CUET, UG, PG, and any PhD entrance test. So let us see. So we have discussed that Lagrangian is basically QK dot and T, where generalized, which is, so this Lagrangian is basically function of generalized coordinate, generalized velocity, and time explicitly. So what is equation of motion? So we have Lagrangian equation of motion. Lagrangian equation of motion, which is, I am not going to discuss the details of derivation, just we have just information. This is d by dt of del L upon del qk dot minus del L by del qk, which is equal to 0, and we have another equation d by dt of del L upon del qk which is qk. I will tell you the details of this right hand side in later lecture, but we will only focus on this. So there are two types of equation of motion. One is this one, d by dt of del L upon del qk dot. So this is Lagrangian equation of motion, is basically partial second order differential equation, and the solution of this differential equation will give us the trajectory of particle, or dynamics of particle, or mechanics of particle. See, this is second order differential equation. If you solve the differential equation, so the solution, we have some solution, and that solution will tell us the exact trajectory or trajectory of our dynamical system. Trajectory means exact instantaneous position of particle at, what is the position of particle at a time t equal to 0 and at any later time. So we will see this. So this is for conservative system. We have two different kinds of Lagrangian equation of motion. This is for conservative system, and this is for non-conservative system. This is for non-conservative system. Conservative system means force derived from the potential. Non-conservative system means velocity dependent potential. Velocity dependent, mathematically we can say that for a non-conservative system means velocity dependent potential. This is simply position dependent potential. Potential, or we can say that force derived from the potential. For a conservative system means force derived from potential. Means if we have profile of k by r square, for example, so this system is known as conservative system. This system is known as conservative system. So charged particle in electromagnetic field. So we have velocity dependent potential. In that case we have a velocity dependent potential. So that system is non-conservative system. So if velocity dependent potential, if we have velocity dependent potential, then that system is non-conservative system. And if we have potential which is function of only position, or which is function of only qk, if we have potential which is function of qk and qk dot also, mathematically we can say that if our potential has profile only which depends upon only position or radial dependency, or qk which is only function of generalized coordinates, and in this case our potential is depends upon generalized coordinate as well as generalized velocity. So this is velocity dependent potential. In some situation we have a profile of Lagrangian in which the potential is velocity dependent. So in that case we will use this equation, and that is for non-conservative system. But in this lecture we will only focus on a Lagrangian for a conservative system. So this is a Lagrangian equation of motion for conservative system. This del L upon del qk dot is qk dot is velocity, means differentiating. What does mean? This means differentiating the expression of Lagrangian with respect to velocity partially. This is differentiating Lagrangian partially with respect to generalized coordinate. This is the meaning of partial differentiation. So now if we have a Lagrangian expression or Lagrangian equation of motion, then how to obtain the concept of, how to analyze the concept of generalized momenta and cyclic coordinates. So concept of generalized momenta. Momentum or momenta. If our Lagrangian, which is having a profile which is function of generalized coordinate, generalized velocity and time, then this del L upon del qk dot is simply pk, and this is our generalized momenta. This is the general profile of generalized. For any given expression of Lagrangian, we can find out the generalized momenta, which is del L upon del qk dot is simply pk. This is pk is generalized momenta. It could be anything. I have already explained the meaning of generalized coordinate. Generalized coordinate is basically number of independent coordinate required to specify the motion, and it could be any quantity. It is not necessary that it has only dimension of length. It has dimension of velocity. It has dimension of force. But once we fix the generalized coordinate, corresponding generalized velocity automatically fixed. If the generalized coordinate is length, then our generalized velocity is length dot dl by dt, means dr by dt, means it is velocity. If our generalized coordinate is momenta, if it is linear momenta, simply p, then our generalized velocity is dp by dt, means rate of change of linear momenta, which is force. So depending upon the situation. So this is known as generalized momenta. Now concept of cyclic coordinate. We have another important concept in this Lagrangian dynamics, that is cyclic coordinate. What is cyclic coordinate? So in any situation, and how to obtain or how to identify or how to recognize whether the given system or whether the given dynamical system or for a given profile of Lagrangian, our dynamical system have a cyclic coordinate or not. It has cyclic coordinate. If we have a profile of Lagrangian, so in that profile, how to identify or how to recognize that for this given Lagrangian or corresponding to this Lagrangian expression, do we have a cyclic coordinate or not? And the meaning of this cyclic coordinate is very important, because it tells the information about the constant of motion, whether our system is having a constant of motion. It means if our system depends upon x, y, z coordinate system or r, theta, phi coordinate system. So with this constant we can say that, because these are independent coordinate. In classical mechanics, these generalized coordinate means these are independent coordinate. So we can predict that whether our system having constant of motion in which coordinate system. It is not necessary that our system is cyclic in all coordinate system. In some situation it is, if cyclic in x, it means corresponding momenta is constant, that is px. So system, our dynamical system is conserved in or constant of motion in px, but it is not necessary that it is also constant in py coordinate system corresponding to y coordinate system. So let us analyze that. So if in any situation, in any situation, if we have del L by del QK, if we have a profile of L in which our del L upon del QK, and this QK is anything, it could be x, y, z, it could be r theta phi, it could be r theta z, depending upon the system, that which coordinate system we are dealing. So if this del L upon del QK is 0, so what we have? What is the expression of our equation of motion? Now putting this value in this equation of motion, so this is d by dt, which is del L upon del QK dot is minus 0 is equal to 0. So this part is 0, this part is 0. So what we have? We have simply, let me write it here, d by dt of del L upon del QK dot, which is equal to 0. Now integrating both sides with respect to t. So what we have? This side is 0, so this side becomes constant if you will integrate. So our del L upon del QK dot is constant. And what is our del L upon del QK dot? This is simply generalized momenta. This is simply Pk. So Pk is constant. So this Pk is constant. So now we can see that now this k is a running index. It has I1. It is profile of x, y, z. This kk could be anything. It is px, py, pz, pr, p theta, p phi, pr, p theta, p phi, pz, depending upon which coordinate system we are looking. So this pk is constant of motion. This pk is a constant. So with this we can say that if this pk is constant, so corresponding coordinate is a cyclic coordinate. It means if our pk is constant, if this k is, so this is means in nutshell we can say that this is the way to derive the or obtain or recognize the constant of motion. So constant of motion with this, and it's all about the Lagrangian equation of motion, which is this one. This is for conservative system, and for concept of generalized coordinate is simply if our del L upon del QK dot is 0, del L upon del QK dot is Pk, this is known as generalized momenta. And cyclic coordinate, if our del L upon del QK in a given Lagrangian, if our del L upon del QK is 0, so corresponding momenta is conserved. So we can say that if any situation our del L upon del QK is 0, so our corresponding momenta is constant. So that motion is constant of motion, and that coordinate is known as cyclic coordinate. So let us see how to find out the concept of generalized momenta and for a given Lagrangian. If we have a profile of Lagrangian, for example, if our, let us write the Lagrangian expression in Cartesian coordinate system. What is our Lagrangian? I have already explained. So 1 by 2 m, basically our L is t minus v. So this is mx dot square plus y dot square plus z dot square minus v, x, y and z. So find out the generalized, corresponding to this Lagrangian, find out the generalized momenta and check whether this Lagrangian is in having cyclic coordinate or not. So first, generalized momenta, which is del L upon del QK dot, which is PK. And what is our K? What is our QK? QK is simply x, y and z. Our QK is simply x, y and z. So in this case we have three different profile of del L upon del QK. So del L upon del QK dot means del L upon del x dot, del L upon del y dot, del L upon del z dot, because our k is x, y and z. This is px, this is Py and this is Pz. And what is our del L upon del x dot? It means differentiating L partially with respect to x dot. So this and the beauty of this partial differentiation is that if you are differentiating partially with respect to x dot, then rest will be 0 or rest will be treated as a constant, and if you will differentiate it will give us 0. So now differentiating this L partially with respect to x dot. So del L upon del x dot is twice of x dot. Twice of x dot. So what is our del L upon del x dot, which is 1 by 2 m twice of x dot. Because in and what about this potential? This potential is in x, y, z. So if you will differentiate with respect to x dot, it will give you 0. So this is this. This 2 will cancel out, and what we have? Mx dot. Mx dot. So this is simply Mx dot. Similarly, this is simply My dot. This is simply Mz dot. Differentiating partially with respect to z dot, del L upon del z dot will give 2z dot, and 1 by 2m is outside, so 2 will again cancel out, and what we have, let me write it here. Del L upon del y dot is 1 by twice of m 2y dot, and del L upon del z dot is 1 by 2m 2 z dot. So this will give my dot, this will give mz dot. So our px is mx dot. So this is the generalized momenta which is in 3 different coordinates, because our qk is in qx, x, y, z. Our qk is qx, y and z. So del L upon del qk dot means del L upon del x dot, del L upon del y dot, and del L upon del z dot, because we have 3 different coordinates, and this q, that is why this qk is known as generalized coordinate, because we can express our qk in different coordinate system. So this is the way to find out the generalized coordinate momenta. So we have 3 different generalized momenta, px, py and pz, whose and corresponding value is mx dot, my dot and mz dot. X dot is dx by dt, or you can write mvx, mvy and mvz. Now what is cyclic coordinate? Second concept of cyclic coordinate. So what we have to do? We have to simply check that in this given Lagrangian profile, this corresponding to this dynamical system, do we have a cyclic coordinate? So to check whether this Lagrangian, in this Lagrangian, whether the cyclic coordinate exists or not. So what we have to do? We have simply check del L upon. So what is our step? Check del L upon del qk is 0. If del L upon del qk is 0, so what is del L upon del qk? Means we have to check del L upon del x, del L upon del y and del L upon del z, because our qk, what is our del L upon del x? So if you are differentiating with respect to x, so what does mean it? It means this part becomes 0 and we have this part. So what is our, this is minus del v by del x, x, y and z, del v y upon del z, and this is minus del v x, y, z by z, which is not equal to 0, not equal to 0, not equal to 0. So no cyclic. So we can say that in this case our del L upon del x is del v by del x, because we have to differentiate partially with respect to x. So there is no x expression, but in potential we don't know. In potential there is a function of x, y, z. So if you will differentiate potential partially with respect to x, y, z, what we will have? We will have del v by del x, del v by del y, del v by del z, and minus sign is there, so that is why minus sign comes into this picture. So our del L upon del x is minus del v by del x, del L upon del y is minus del v by del y, del L upon del z is minus del v by del z, which is not equal to 0. If it is 0, then we can say that okay, yes, there is a cyclic coordinate. But if our del L upon del qk not equal to 0, in this case our del L upon del qk is not equal to 0, then there is no cyclic coordinate. If it is 0, then we can say. If it is not, but fortunately in this case there is no cyclic coordinate. So there is no constant of motion. There is a no constant of motion. So this is the way to find out the concept, to find out the cyclic coordinate, to check whether the given Lagrangian is having a cyclic coordinate, or this is the way to find out the concept of generalized momenta. It's all about this. In next lecture we will discuss few examples to analyze the behavior of generalized coordinate and corresponding cyclic coordinate and corresponding generalized momenta. Thank you.